extent, we can say a little more. But here, yeah, we only evaluate the gradient.
Okay, great.
Gradient norm.
Okay. Thanks again for Kevin. It's a very nice talk.
Thank you.
Our next speaker is Yihan Zhang. Yihan is a postdoc at the Institute of Science and Technology, Austria, and he was a postdoc at Technin, and his research interest mainly lies in information theory, coding theory, and statistics. So let's Yihan, can you share your screen? You are muted.
Yeah, just a sec. By the way, am I properly audible?
Yeah.
Okay, just a second. Let me try to share my screen.
Okay.
Can you see my slides?
Yeah, sure.
Okay, cool. So yeah, thanks for the introduction and thanks for the invitation. My name is Yihan. This talk is about coding against adversaries. More specifically, it's about adversarial channels. In its largest portion, it's going to be a survey talk. I'm going to introduce several models and state some of the recent results along these lines, but I'm not going to prove any of these things because I don't have the time. But basically, this serves as an invitation to call for people to work on this topic because I think there are many interesting questions to be solved in this field. Okay, so let me start by introducing the players of our game. So in any like channel coding problem, with or without adversary, we have at least three players: the Alice, which is the transmitter, and Bob, the receiver, and somebody who is bad in our scenario, which we call James. He's actually an adversary who is trying to maliciously corrupt the communication from Alice to Bob. So for any adversarial channel problem, if you look at it at a distance, then they all look roughly like this. So Alice had some message in mind and she wants to transmit it, but unfortunately the channel is noisy. So she just introduced some redundancy and transmitted that through the channel. That's called the code word. But unfortunately, the channel is actually governed by some bad guy, which is James. He can insert some adversarial noise, which is carefully designed to prevent communication from happening. And then Bob, receiving the noisy observation, wants to guess or decode the transmitted message by Alice. So that's the basic setting. Here, I want to highlight one thing, which is the power or limitation of the adversary, what he knows and what he does not know. So if the adversary does not know anything about the particular transmission in the channel by Alice, then he's said to be oblivious. On the other hand, if he knows exactly what's transmitted by Alice, then he's said to be omniscient. These two things are kind of extreme, and they are two very important models. And in this talk, I'm going to talk about these two things and some other models that lie in between these two extremes. So let's start from the omniscient extreme. So mathematically, this is a channel model. We have this channel W. It takes two inputs, which is the input vector X and some noise vector S, and it outputs some Y. The way it does so is that it takes input X and S and acts component-wise on each component of Xi and Si and output Yi in an IID manner. So basically, okay, for now you can think of this function as a deterministic function, but things can be generalized. But for simplicity, let's stick with deterministic function. But importantly, this S is not IID generated. It's some adversarially chosen stuff. And these X, S, and Y, they can be over any general alphabet, not necessarily binary or something. It can be anything finite. And for the sake of generality, which is going to be important when I talk about things later, so I want to further impose constraints onto the channel input X and the noise vector S, because there are many channel models for which without these constraints, they become just trivial. So the way I impose constraints is in terms of the type of these vectors. For those of you who are not familiar with types, this is nothing mysterious. It's just nothing but the empirical distribution of a vector over some finite alphabet. Let's say I have a ternary alphabet ABC and I have some vector over ABC which looks like this. Then the empirical distribution is tau x, which I call the type of x. It's just the frequency of each symbol appear in X. So similarly, if I have a pair of vectors, I can talk about is joint type or joint distribution empirically. That's nothing but a matrix. It's a joint distribution. And more generally, if I have multiple vectors, I get a tensor. So yeah, now back to the model. The way I impose constraints is in terms of the type. So let's say I give you a convex set of distributions over X, which is the input alphabet. And my constraint is that given this set, I want any input of the channel, which is X vector, the type of X should lie within this set. That's my constraint. And similarly for S, I fix some arbitrary convex set lambda S, and I want tau of S to lie within this set. Convexity is not super important, but it kind of avoids the wacky behavior of the channel. So let's stick with this assumption. So given such a so general channel, probably the first question we want to ask is that when is the capacity positive? Surprisingly, this question is not known to this generality until very recently. It was shown in Wang et al. In a recent paper by Wang et al. That the capacity of this channel is equal to 0 if and only if the following thing happens. So what is this? So this is an equation involving two sets of joint distributions on X. Basically, these are two sets of joint distributions containing distributions of the form P of x1, x2, okay, on two variables. And what are they? So this K on the right-hand side, these are bad distributions given by the channel. So for any given channel specified by these things, I can compute this K in the following way. Let me define this operationally first. So this K captures the following thing. So let's say I have two vectors or two code words. If they are confusable, then this certifies that the code is not good. So what do I mean by they are confusable? It means that there exists some S1, S2 satisfying constraints, of course. Then under the action of the channel, they can reach the same Y. Then receiving Y, the decoder has no idea whether X1 or X2 was transmitted. So this is a bad situation, and it's actually not hard to see that this condition is if and only if a code is good, if and only if there's no pair that is confusable. Now, note that this notion is permutation invariant just because the channel acts on each component of X and S independently. So if I apply permutation, was confusable remains confusable, was not remains not. So I can, without loss of generality, therefore just look at their type. So I collect all types of confusable pairs of X1, X2 and call that K. Okay, so this is basically the set of distributions Px1, x2, which satisfies this structure, basically. So this is a complicated equation, but it's really just describing the previous structure. That's the right-hand side of the equation, K. It's given by the channel. Given any channel, I can compute it. Now, what's the left-hand side? This is some special set of distributions, which I call good distributions. Actually, they have a name called completely positive distributions or matrix. They look like this. So they are convex combinations of product distributions. So it's not too hard to see that if I have product distributions, then it's easy to construct good codes from them, just because we like sampling codes IID from certain distributions. So if I have product distribution, I have good codes with high probability. But here, this is a slight generalization of that because I can take convex combinations of product distributions. The intuition here is that it has some operational meaning that we call coded time sharing. So this PU actually corresponds to some time sharing sequence. So this set of distribution is independent of the channel. It's well defined. It's just a sum set over there. So now the theorem says that if this is the ambient space, this pink thing. Now, given any channel, I can compute K, which is a certain set of distribution. And I compare this K with CP, which is always there, right? If it turns out to be this case, that CP is not a proper subset of K, then I claim positive rate is possible. Otherwise, if K happens to cover the whole CP, then this is the bad scenario. I claim no positive rate is possible. So this achievability result is perhaps not too hard. I have just alluded to this proof because it really just follows from random coding argument. But this side is highly non-trivial, which I'm not going to get into, but it turns out this characterization is extremely useful. It leads to a burst of results that I'm going to flesh out. So what I have just mentioned is the 0th order characterization of the capacity of the channel. But in fact, it goes beyond that. We can also get some first order bounds on the capacity itself. We can get lower bounds using random coding with expurgation. And we can also get some EDS Pasaligo type bound using using some combinatorial techniques. But you don't have to know any of these things, but you don't even need to read these formulas. But I just want to show you that first order bounds are actually possible. I should mention that to characterize the capacities, given the current techniques, is basically impossible, because even for very, very simple bit flip channels, the capacity is widely open. It's actually equivalent to sphere packing problem in Hamming space. So there is no hope to get that for now. Now, I have talked about the basic omniscient channel, which is one extreme of our spectrum. Let's go slightly beyond that. Let's go to list decoding, but again for omniscient channels. So what is list decoding? Now, instead of insisting on the decoder output a single unique code word or message, doesn't matter, I allow him to output a list of code words, let's say a small list, 3 or 5. But the requirement is that the list should contain the correct one, the correct answer. Otherwise, this list is just meaningless. So the model is exactly the same as before. It's just that I relaxed the decoding goal. And basically, every bit of the previous theory can be pushed to this setting as well. And we also have some zeroth order characterization of the list decoding capacity, which looks like this. Now, these things are the tensor version of the previous previous sets of joint distributions. They are now tensors. So yeah, I'm not going to get too much into this. And also we can get upper and lower bounds using sort of standard techniques, but they are actually not that simple. Now, in fact, these bounds, they meet each other once we send L to infinity. Basically, for large L, we get the exact list decoding capacity. Okay, so that's one extreme of the spectrum I mentioned, which is the kind of the coding theoretic model. Now let's go to the other extreme, oblivious model. Let's directly talk about oblivious list decoding. So just to recall, in oblivious model, the adversary does not know what's transmitted by Alice. So, and again, let's look at the list decoding version of this problem. So surprisingly, the previous result on omniscient channels is actually useful here for some technical reasons. But basically, the main result here is that we can exactly characterize the critical list size. What do I mean by that? This L star is the smallest list size above which the list decoding capacity is strictly positive. So clearly, if I increase L, it's going to be easier for Alice and Bob to achieve positive or larger rate. So the critical value of L star is equal to something called L star CP. Okay, from now on, I'm not even going to give you the formula because I don't have time to properly define the quantities involved in these expressions. But basically, these things can be exactly written down explicitly, and they are independent of the block length. So, and the idea actually comes from the omniscient result, curiously. So now, I have talked about two extremes, the omniscient extreme and the oblivious extreme. Now let me talk about two additional models which are actually strictly lying in between these two extremes. So one of them is called myopic channels. So this channel looks like this. So it looks almost like the omniscient channel. So the adversary does know something about the transmission, but it's through some noisy channel. But this noisy channel is just some purely random channel in Shannon's sense. So let's say this is just some DMC, for example, or some Gaussian channel. Therefore, we call him myopic because he doesn't know exactly what's transmitted. He has some knowledge, but not exactly. So here, this problem turns out to be pretty difficult. Recently, there is some results on rate positivity of this channel and some results on capacity bounds, but any of these results are not expected to be tight. So there are a lot of things to be done here. So, but I should say one more word about this thing, which is that many of these results actually meet, or you can say collapses, when we specify these things to myopic erasure channels. What is this? This is the channel that the Alice to James, the channel from Alice to James is a binary erasure channel with erasure probability Q. This is a random channel, by the way. And the main channel from Alice to Bob is some adversarial binary erasure channel with with Hamming weight P. So this is basically characterized by two parameter P and Q. And the landscape of the theory looks like this. A lot of things is known, but of course, just because this converges to the omniscient model at the end of the day, there's no hope to characterize everything, but we already know quite a lot of this. Okay, so that's the myopic story. Now let me mention the last model, which is the online model, or also known as causal model by information theories. So here, the adversary also knows the transmitted code word, but again, subject to some constraints. What is this constraint? It's the causality. So it's like the adversary can look at the transmitted code word by Alice, but only symbol by symbol. And his design of adversarial error should be on the fly. So he has to design his noise vector S, and in particular each entry Si, depending on his observation so far. Let's say Si only depends on X1 to Xi, but not in the future. So this imposes further constraints onto the model, and things do get much more delicate. And in this generality, for any general online adversarial channel, I believe together with Sid and Michael Engelberg, we have some characterization of this channel, but it's not completely satisfactory in the sense that, first of all, this only works for some reason, only works for a channel with only one constraint on the noise vector. This is just for technical reason that we couldn't handle beyond this particular constraint. And also, the capacity expression is multilateral, so in principle, it's not evaluatable actually. But I mean, even this is already non-trivial to obtain. And again, this relies on list decoding, which I talked about before, and also omniscient confusability or symmetrizability. So yeah, these things are all related in some technical sense. Now, finally, I have, still have some minutes. So let me briefly mention this thing. So in some particular scenarios, some of the coding schemes I mentioned before actually can be made computationally efficient. What do I mean by efficient? I mean the encoding and decoding procedure can be made run in polynomial time, in n, in the number of transmissions. So here are two samples of this type of results. One is for oblivious channels. Again, there are some technical conditions called Doplerschen-Stambler non-symmetrizable oblivious channels. Not clear what it means, but it's not important. Basically, for some nice large family of oblivious channels, we can construct capacity achieving codes that are polynomial time encodable and decodable. The idea here, and in fact also for this result, is that we can use stochastic codes with some additional infrastructure to help efficient decoding and encoding. Now, this particular result, here's another sample of this type of results, which is particularly for erasure type channels. For example, for myopic erasure channels, meaning that again, from the channel from Alice to James is erasure, binary erasure channel, and the channel from Alice to Bob is also an adversarial erasure channel, and James is myopic. In this case, we can also construct efficient codes. And also for this online erasure channels, similar things can be done. And here, erasure case is easier because as a component, we have used a lot of list decoding results in these type of theorems. So efficiently list decodable code for errors or other more general error patterns are actually not known. But for erasures, this is trivial because if you want to list decode erasure codes or list decode encoding or decoding erasure codes is actually easy because encoding is just matrix vector multiplication and decoding is just solving linear systems. So erasure case is kind of easy, but I guess we can't push too far from that. So yeah, that's basically the frontier. Now, there's a whole spectrum, as I said, from basically the Shannon's world to the Hamming world. In fact, this is called the paradigm of bridging Shannon and Hamming. So I have talked about very Shannon type models like oblivious channels to very coding theoretic channels like omniscient channels. So, and I also talked about list decoding online channels and so on. But there are actually many more models. For example, feedback channels and two-way channels, things like that. If you make the noise adversary, it suddenly becomes very difficult. And also some adversarial communication over multiple access channels. I think, in fact, the next talk by Nihar is tightly connected to this topic. Okay, so that